We're picking up with homework questions on worksheet 4.4. So let's read our true-false questions carefully here. If f prime of c is equal to 0, then c is a critical number. That would be true no matter what kind of function it is. So the fact that it's a polynomial function isn't too important there. If f prime of c is equal to 0, then it's always a critical number. If f prime of c is equal to 0, for a polynomial function, then c is the coordinate of an extremum. So just because, and remember f prime of c equals 0 means that f has a horizontal tangent. F has a horizontal tangent. So does that mean it has to be an extremum? Well, that's true much of the time, but remember our x cubed graph where we have a horizontal tangent at what we've called a saddle point. So the saddle point would be our counterexample. So just because you have a horizontal tangent is not enough. The first derivative has to change from positive to negative or negative to positive. Number 16, if we have a point that is given as an extremum, then c must be a critical number or a closed endpoint. That is definitely true. We know that our extrema can only happen at those two places. And if f of c is a local extremum and the first derivative exists, then does it have to have a horizontal tangent? So if the first derivative exists, this rules out cannot be a corner. Cannot be a corner or a discontinuity. So then we have to have it as a horizontal tangent. So 17 is true. In 18, if c is the x-coordinate of an extremum of a function f, then does f prime of c have to equal 0? No, f prime of c could be undefined. Could, if I could spell, could be undefined. A good example would be our absolute value function. Doesn't it have an absolute minimum right there at the corner where the derivative does not exist? So I think we'd have to go with false for 18. In 19, if c is the x-coordinate of some kind of extremum and f of x is equal to 2/3, we just did that seagull graph on the previous page, then f prime of c has to be 0. And that was exactly not true. We actually, at f of x, which looks like our seagull, we're actually going to have a cusp. So there's going to be no derivative. F prime is not going to exist at that minimum point. So there's our counterexample. In 20, if f is continuous over a closed interval, then there has to be an absolute max and there has to be an absolute minimum. That is definitely true. That's our extreme value theorem. In number 21, if f is continuous over an open interval, then does it have to have an absolute max and an absolute minimum? No, not if it has open endpoints. So that would be false. So a very simple counterexample would be this diagonal segment, which is continuous on an open interval, but its maximum and its minimum would have occurred at the endpoints had it been a closed interval. So there's our counterexample for 21. 22 is our horizontal segment or horizontal line. So does it have a local maximum when, let me get back where I was. And our horizontal line would have 5 as its maximum everywhere. So not just at that x-coordinate, but at every x-coordinate. So we'll go with true for that one. All right, find the critical numbers. So we have to look at where the derivative is equal to 0 or where the derivative is undefined. And if we set this to 0 and factor, and we could divide the 3 to the other side, by the way. Doesn't have to stay there. So x plus 4, x minus 2. So our critical numbers would be 2 and negative 4. And so I just lost my page, but I'm back again here. So it'd be nice if you rewrote your critical numbers smallest to largest, and you'll see why as we do some future problems. But it's certainly not wrong, whatever order you get your critical numbers. All right, 24. To find our critical numbers, we need to do the derivative, and this would require a quotient rule. So we'll have our low d high minus our high function d low. And let's see what we've got here. P squared plus 4 minus 2p squared plus 2p. And then we're going to have to clean that up to set it to 0. So our numerator, negative p squared plus 2p plus 4. And I'm not sure whether this was intentional or whether perhaps I typed the problem wrong, but this numerator doesn't look factorable to me. So where is the numerator? Ph prime is equal to 0. We would have to set the numerator to 0. And I think that means quadratic formula. So we would have the opposite of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So it looks like our discriminant under the radical is a 20. So we've got negative 2 plus or minus square root of 20. Can I write as 2 square root of 5 all over negative 2? So our 2p values here, if we divide each of these, we would have a 1 plus or minus the square root of 5. So that's where our derivative is equal to 0. And is our derivative ever undefined? So we're going back to our derivative. So h prime of p is undefined when the denominator is equal to 0. But I don't think that's going to happen here, since p squared plus 4 squared is never equal to 0. It would always be a positive value. All right, so our critical numbers then, if I go back up here to give my final answer, our critical numbers were just 1 plus and minus the square root of 5. So that maybe was a lesson that occasionally you'll have to do quadratic formula. Won't happen too often during test time when your time is short. All right, so a couple more here, critical numbers. So the derivative of cosine is negative sine. And here we have to do our power rule. So bring down the exponent, and then we have to do our chain rule. Derivative of sine is cosine. So when is this equal to 0? Well, let's find out. Let's factor a 2 sine of x. Let's factor the negative 2 maybe. You could put the negative with the other term, I guess. It doesn't really matter. If we factor the 2 sine x, we'd have negative 1 plus cosine. So this is equal to 0 when sine of x is equal to 0, or when the other factor is equal to 0. So when you have two factors, when is the product equal to 0? When one or the other of the factors is equal to 0. So we can specify all of these values. Sine of x is equal to 0. at all values of n pi. So of 0, 1 pi, 2 pi, 3 pi, 4 pi, and so on is what we mean by n. So n represents any integer. And where is the cosine of x equal to positive 1? Well, that happens to be only this same place. So the cosine of x is at, if we were answering this individually, it would be at 2n pi. So it would be at 0 pi, 2 pi, 4 pi, and so on. But this one certainly takes care of. N pi covers 2n pi. So I think that could be our answer for our critical numbers at all multiples of pi. All right, and here, let's see how you might want to think of this. You could think of it as a quotient rule, natural log of x over x squared, or you could leave it the way it is and do it as a product rule. So I think I'll stick with the way it's originally written and do a product rule. So we'll have the first glob times the derivative of the second glob, and it's a plain old x, so we don't need a chain rule, plus the second glob times the derivative of the first would be a power rule, negative 2x to the negative third. And if I factor out, well, actually, I guess let's rewrite this. Notice this is x to the negative 1. So let's think about this one. Algebraically, do you see they both have an x to the negative third here? And then we could bring that negative 2 out here. So when we want to factor this, we can factor out our x to the negative 3, and we'll have 1 minus 2 ln of x. Or if you prefer, 1 minus 2 ln of x over x cubed. So our critical numbers, so we know f prime of x is undefined when the denominator is 0, so that would be when x is equal to 0, that would make the denominator equal to 0, and f prime of x is equal to 0 when the numerator is equal to 0. So when is 1 minus 2 ln of x equal to 0? Well, that would be when ln of x is, maybe I shouldn't do it that way. Let's move that to the other side so we don't lose anybody. When ln of x is equal to 1/2. And remember what that is. The base is e, so this means that ex would be equal to e to the 1/2 or square root of e. So our critical numbers for this problem were 0 and the square root of e. All right, now we've got some global extrema questions, and notice we have a closed interval. So let's practice here. Remember this name, closed interval test. So remember that global extrema can happen at critical numbers or at closed endpoints. So we've got to find more critical numbers. So let's find the derivative. And it's never undefined in this case, so when is it equal to 0? So you don't have to show all of these algebra steps. Divide by 6, and we would have plus or minus 3. So now we have to do our closed interval test and find f of x at the endpoints and at the critical numbers. Now notice that negative 3 is not in the interval. So not in the interval from 0 to 4, so we only have to test 3 values here. And remember to plug them into the original function. So we would come up with, and it's perfectly fine in your homework if you grab a calculator for this. I think I have 5 and 113 and 93. So we have a global min, of 5 at x equals 0, and a global max of 113 at x equals 3. Whoops, sorry, I'm getting a little jump here on my page. All right, 28. Again, every time you are asked for global extrema on a closed interval. So we've got to find our f prime of x. So we have to do quotient rule again. Low d high minus high d low over low squared. So notice again our denominator is always positive. So there's never going to be a value where the derivative is undefined. So we just have to set the numerator equal to 0 to look for critical numbers. And that numerator, if we set the numerator to 0, we would bring out the 2x in the numerator. And we'd have a x squared plus 4 minus x squared minus 4. So the x squareds are going to cancel there. So we would have a 2x, and then we would have an 8. So when is that numerator equal to 0? That would be when x equals 0. When x is equal to 0. So that's our only critical number, I believe. So then we would have to do our closed interval test and find out where we get our absolute max and min. So we need to look at the y coordinates. And remember that you're looking for the y coordinates of our original function. So if we put negative 4 in there, we would have 16 minus 4 or 12 in the numerator and 16 plus 4. So we could reduce this, cancel by 4. If we put 0 in, we'll get negative 1. In other words, we'd get a negative 4 over a positive 4. And it's an even function, so if we put 4 in, we'll get the same thing that we did for negative 4. So we've found out here that we have a global minimum of 1 at x equals 0 and a global or absolute max of 3/5 at x equals plus and minus 4. So include both places. So you can see how that would really help you when you have to graph a function if you already know its extrema. All right, let's see what this one is. This is a little hard to read. So I think this is meant to be an exponent here. E to the negative x squared over 8 is our exponent. So I see a product rule. The first function times the second function. So our f prime will be the first glob times the derivative of the second glob. The derivative of e to anything is e to that anything times the chain rule on that anything. So now let's think about the derivative, and that exponent you might like better if you think of it this way. Do you see that that's the same as negative 1/8 of x squared? So its derivative would be a negative 1/4 x. So there's our uv prime, and then plus our second glob times the derivative of the first glob is just 1. The derivative of x is just 1. All right, so we could write this in factored form. We could bring that e to the exponent out of both terms, and we would have a 1 left from the second part, and we would have a negative x squared over 4 from this part. So this reminds you why sometimes right away I've said why not factor the fraction out right away. So watch what happens now, how much easier this is if I also factor a negative 1/4 out of each term. So divide by negative 1/4 is the same as multiplying by 4. So negative divided by negative. So I wish I had done that right away. When I brought out the e to the power, I could have brought that fraction out. Why is that helpful? Well, remember what we're doing. We're looking for the places where this derivative is equal to 0. So now I can easily see its factors. Okay, so our question is, where is f prime of x equal to 0? And certainly you guys can see the negative 2 and the positive 2. Is e to a power ever equal to 0? Is this first factor ever equal to 0? Well, e is 2.718, so think about taking 2 and raising it to a power. Will it ever be equal to 0? And that is definitely not. So we get negative 2 and positive 2. Is this ever undefined? And there is no value of x that would cause any trouble here. So these are our only two critical numbers of negative 2 and positive 2. And now, goodness, we still have to go back and find our extrema. So we have to check at our closed endpoints. I've already forgotten the problem. So our closed endpoints are negative 1 and positive 4. So the only critical number that we have to worry about is the 2. So this one is not in the interval. So this is not in the domain that we're interested in. So we don't have to worry about it. So now we have to go up to that original function and put negative 1 into that. Well, that might you might not like that original function. Let's rewrite it so I can see it here. F of x is equal to x e to the negative x squared over 8. So if I put negative 1 into that function, so we would have a negative 1 e to the negative 1 squared is positive 1. So we would have e to the negative 1/8. And you could approximate that. So you could grab your calculator, and let me pause and do that. I have negative 0.882. All right, and then when we would do f of 2, it's going to look like 2e to the, and now when we square the 2 for the x, we'd have 4 over 8, so that's going to be 4 over 8, is 1/2. And again, to see the value, we could approximate that. And punching that in, I get 1.213. I hope my calculating is correct. You can adjust if not. And then when we put 4 in for x, square it, we'll have 16 over 8. So that would be 4e to the negative 2. And we'll come up with 0.541. So now we've located our global max and global minimum. So we should clarify. Final answer here. I used up a lot of space here. Global max of approximately, if you wish, negative 0.882 at x equals negative 1. And a global, whoops, sorry, I wrote max, but I picked the minimum. Let's just change that. That's our global minimum and global max of approximately. And you could use these exact values from this column if you wish. Nothing wrong with the exact values. There's our global maximum at x equals 2. All right, so almost there. Sorry. These are some Good derivative practice. F prime of t. Before we can find our critical numbers, this one, let's see if it'll go faster. The derivative, the 2 can come out of the derivative. The derivative of cosine is negative sine. No chain rule needed. The next one has a glob, so the derivative of sine is cosine of the glob times the chain rule on the 2t. So we could factor, oh my goodness, a 2 out of this, and we'll have cosine of 2t minus sine of t. So, wow, here's some trig review. What do you know about a double angle formula? Double angle formula. So this is where you would pause if you do not remember this, and you'd go look it up. All right, so let me find the double angle formula to make sure I don't write it backwards. Or should we give this a whirl without changing that? So double angle formula. Let's try setting this to 0 first and see if we can just hammer this out. This is going to be equal to 0 when cosine of 2t is equal to sine of t. Let's think about that. Where is the cosine of twice the angle equal to the sine of the angle? I don't suspect you like this plan any better, but it's all excellent review. There's our sine wave going from 0 to 2 pi. What happens here? The period. Remember 2 pi over b. So our period length here is only 1 pi. So our cosine wave is going to start and end. Let me do our cosine graph. Our cosine graph is going to have the period cut in half. So it is going to hit its minimum here. So I do this only as a reminder for you. So where is the cosine of twice an angle equal to sine of the angle itself? And can you come up with that visually, or can you just think about that from our special triangles? So this is going to happen at pi over 6, and then you can test that out. So if you put pi over 6 and doubled it, that would be pi over 3. So you maybe could have come up with that just by trial and error. Or you could go back to my idea of looking up the double angle formula and changing that. All right, so of all of those methods, you've got a choice here. So pi over 6 is our critical number, is what it comes down to after a lot of discussion of trigonometry. So our closed interval test, remember that we have to find the biggest and the smallest, and our interval is from 0 to pi over 2. So, oh, that's why this, sorry, I should have explained this 5/6 pi here. 5/6 pi would also be a critical number. Okay, but it's outside our interval, so we only want to go from 0 to pi over 2. So I didn't care about the 5 pi over 6. All right, so let's go back to our original function and put these in here. So we want 2 times the cosine of 0 is 1, and the sine of 0 is 0. So our first y coordinate would be 2. Now let's put pi over 6 into the original function, and the cosine of pi over 6 is square root of 3 over 2. So when we double it, that'd give us a square root of 3. And when we double pi over 6 here, that would give us the sine of pi over 3. And the sine of pi over 3 is square root of 3 over 2. So we could round that value off. You could do these completely with your calculator as well. And at our last value of, let's Get back into focus here of pi over 2. Cosine at pi over 2 is 0. And when we double pi over 2, 2 times pi over 2 is pi. And the sine of pi is also 0. So we'll get 0 there. All right, so what do we know about this value? Is this value bigger than 2? It sure is, since the square root of 3 is 1.7, so approximately. So we'd have 1.7 plus approximately 0.85. So this is actually our global maximum, our global max. And you could have rounded it off. You didn't have to leave it in that exact form. But I'm getting ready to quit here, so this is good enough. The exact form is never a problem, and our global minimum of 0, sorry, I just shrunk my page here, at x equals pi over 2. Hallelujah, we made it. Wow, what an assignment. Sorry, guys.